Good evening. We're going to be we are going to do some problems or numericals from electrostatics, chapter 2, which is basically electric potential and capacitor. So we're going to solve simple problems. So again and again, I'll emphasize the fact that please learn to do physics problems in a simple way. No, it's not complicated. It's just that you need to know what to do, how to basically apply the formula, what to write down, how to visualize the problem. Main issue is visualizing the problem. Okay, let's just take simple problems and visualize it and also write down the formula and solve it. Okay. And also some arithmetic, how to do arithmetic technique. Simple, how to simplify that, what to calculate, what not to calculate. So these are the things that we will learn in the process. Okay. So let's take the first question. I'm going to basically take the questions from NCRT one. So it will be easy for you to keep track. So let us look at the first question. So two charges, so you can write down two charges, 5 into 10 to the power of minus 8 coulomb, 5 into 10 to the power of minus 8 coulomb, and minus 3 into 10 to the power of minus 8 coulomb, minus 3 into 10 to the power of minus 8 coulomb are located 16 centimeter apart, are located 16 centimeters apart. At what point on the line joining the two charges is the electric potential zero? Take the potential infinity to be zero. So we want to find out at what point on the line joining these two charges electric potential is zero. So let's just write down the diagram. Always start with the diagram. You have two charges. Let's say charge 1 here, which is 5 into 10 power minus 8 coulombs. And on this line, we have one more charge here, which is minus 3. One is a positive charge, another one is a negative charge. Two charges are. Now, these two charges, line joining, this is the line joining these two charges. Line joining in the sense that it may extend on both sides. Okay. So, where they are not asking where in between these 2 points the electric potential is zero. That is not the question. Where on this line? And they have also hinted saying that instead of writing point, they have written points, that there it may be zero more than 1 point. Okay. So let us see how it is the case. So whether it is true or not, we will figure out. Okay. Now, first point basically is how do we find the electric potential? We already know that we can actually find the electric potential using a basic formula. Electric potential due to a point charge, we know that V is equal to Q in KQ by R. So K here is 9 into 10 power 9. I will again remind you that K is same as 1 divided by 4 pi epsilon naught, where epsilon naught is permittivity. However, please understand that this permittivity value is known, 8.85 10 power minus 2 minus 12. So if you use that and calculate all this, it will take more time. So using K is somewhat easier for our purpose. So K is the reciprocal of 4 pi epsilon naught, and Q is the charge, and R is the distance, not distance between these 2 points. So this is actually V at certain point P. Okay, somewhere one point is there. On that point, there is a potential. So when you want to find the potential at a certain point, we need to figure out that that potential is due to some charge. So what is that point charge? That we have to write here as Q. And this R is the distance to that point charge. So that means if there is a point charge somewhere here, and I want to calculate the potential at some point here, wherever, maybe here. Okay, this point P, there is nothing at point P. There is nothing. Okay, it is just a place. At that point P, what is the potential? Why is there a potential there? That is because there is a charge here, 3 coulomb or 2 coulomb, microcoulomb, minicoulomb, whatever, some charge is there. So that charge produces a potential here, and we want to find the potential at this point due to this charge. Okay, so now we have to find out, to be able to find that, we need two things. One is how much is the charge and how much is the distance. These are the only two things. So they have to give the charge and they have to give the distance. Now that means basically if you take any point around this, we can find the potential due to this charge. Similarly, you can find the potential due to any other charge also, due to this charge. So potential due to the first charge, potential due to the second charge, we can find out. So let's say this charge will call it as A and this charge will call it as B. Yeah. Now, so we can find out, let's say at some point P here, we can find out potential at P due to the charge at A. Because there is a charge here, there is a potential. And similarly, potential at P due to the charge B, we can find out. So now, if you want to find out total potential at that point, potential being a scalar, we can simply add whatever is the potential from here because of the charge A, whatever is the potential. Let's say because of the charge A, you got potential to be 5. Yeah. Because of the charge B, you got potential to be 2. So 5 plus 2, 7 is the total. You get 5 rupees from somebody, 2 rupees from somebody. Total how much? 7. Right. That's how easy it is to calculate the potential. Only crux is the fact that it can be negative. Okay, one is 5, another is minus 2. In which case, if when you add, it will become 3, not 7. Okay, so the potential, though it is scalar, it can be actually negative. So now in this question, they are not asking you such a direct question of calculating what is the potential at certain point. Like that, they are not asking. They are asking a slightly different question. There are two charges, and these two charges create potential individually, independently in this area, and everywhere we can add and get the potential. Now, when you add like that, okay, and you are only taking basically on this line, okay, they are saying very clearly that they want it only on this line. On that line, let's say you choose some point and find the let's say I will choose some point here and find the potential. So due to this, there is some potential. Due to this, some potential. Now when I add that, when you add that, if it happens to be zero, if it happens to be zero, then we get a zero potential point. They are asking very clearly, potential 0. So which point in between here you will have potential 0? That's a question. Yeah, but they are not limiting the question to that. It's not just about these points in between, but it's also about this side and this side. Is there a point anywhere else where the potential is 0? So these two things we have to answer. So the question that we have to find out, where is, let's say we'll assume that there is a point somewhere here. I will call this point P. Let P be the point at which potential is 0. Correct? Let P be the point where potential is 0. Okay. And this point, we'll take it from here, is at some distance. We don't know the distance. Okay. If we'll take it as variable x, this is x. Okay. The other variable is 16 centimeter. 16 centimeter, basically, if you want to write it in terms of meter, 0.16 meter. So this one is actually 0.16 minus x. That is this. So we don't know x. If we find x, that means basically we figured out that where the potential is 0. So how to find this x? So basically to find this x, we already know what is the potential at this point due to one charge. We can calculate using this formula. Okay, I will call this as charge A, that is 2A, and this as charge B. Correct? This is distance between them D. This has to be written as 0.16 meters. Now we will write here. So look at what we are going to write. Potential at point P. Potential at point P due to A. VPA. So that's my symbol. The potential at point P due to A. We want to calculate. So what did that be? That would be basically nothing but KQ1 by X. Correct? KQ1 by X. So we can write down here K is 9 into 10 power 9. Q1 is 5 into 10 power minus 8 divided by X. This is our VPA. So I want to simplify it a little bit. This is 10 power 9, this is 10 power minus 8. So that would become 10. Yeah, 9 minus 8 is 1. So 10 power 1, which is 10. And this is 9 5 is a 45. 45 into 10 is 450. 450 by 10. So this is basically nothing but VPA. So that is potential at point P due to the charge that is there in A. So I'm going very slow, the first problem, mainly because you need to understand what we are calculating. Don't do it blindly. Just don't keep substituting the values without knowing what is happening. The next thing that we are going to do is potential at this point due to the point P, we will calculate. Potential at that point due to point P, that is nothing but VPB is equal to KQ2 divided by 0.16 minus X. Correct? So this is the distance. Distance is 0.16 minus X. Now you take it as 9 into 10 power 9 into Q2 is, we have written here Q2 or QB, that's called 2A QB. No, I am not using 1 and 2. Let's call it as 2A QB. Take QB. QB is minus 3 into 10 power minus 8 divided by 0.16 minus 8. So this can be written as, this is basically 9 3s are 27. 27 into 10 is 270. Is minus 270. Okay. Why 10? Because 10 power 9 into 10 power minus 8 is 10 power 10 minus 8, which is 10 power 1, which is 10 minus 270 divided by 0.16 minus 8. Okay. So now we got potential at this point due to A and due to B. So we are going to basically add potential at point P is simply equal to VPA plus VPB. Potential at both the points, if you add potential at, due to both the charges, if you add at that point, we will get the potential at that point P, and that would basically be nothing but 450 divided by X minus 270 by 0.16 minus X. Okay, and this has to become equal to 0. They are saying, where is the potential 0? So if this is 0, then whatever the value of x for that, that would be the position where it is kept. Okay. So how to calculate this? So now this is very straightforward. Once we write this, okay, up to this point, we have used physics to write this equation. Now you have to use math to solve this equation. So we can write this as 450 divided by x minus is equal to when 270 divided by 0.16 minus x. Okay. Now I'll tell you some interesting things. Okay. So when we have taken effort to multiply 9 into 5 and got it as 450, correct? Similarly, we have taken effort here to multiply 9 into 3 into 10 and got it as 270. Okay. Now we want to find out how to basically simplify these. So this looks like a big number. Instead of that, if we had kept it as 9 into 5 into 10, and this one we keep it as 9 into 3 into 10. Okay. So I would write it that way. So just show you how it is becomes simple. If you don't immediately do the calculations and postpone it, how it becomes easier. 9 into 5 into 10. Whereas here it is 9 into 3 into 9 into 3 into 10. Minus anyway, I'll taken care of. 9 into 3 into 10. So now what happens, you can see that this 9 goes, this 10 goes, only 5 and 3 will remain. So this whole equation has now become simple. Okay. So 9 into 0.16 minus x. Sorry, I'll write the same equation again here. I'm going to erase this. You have already written it down. 5 divided by x is equal to 3 divided by 0.16 minus x. Okay. This is the equation that we have to solve. So what we will do is we will multiply, okay, this into this into this. So 5 into 0.16 minus x is equal to 3 into x. Cross multiply we do, and here we multiply. Okay. So when you multiply this, this will become 16 fives are how much? You have to remember that multiplication table. Okay. So it is 80. This will become 0.8 minus 5x is equal to 3x. Okay. So now you can see that if I get this one this side, it will become 8x. 0.8 is equal to 8x, or x is equal to 0.8 divided by. Okay. So that basically is nothing but 0.1 meter. X has come as 0.1 meter. So look at this. Total is 16 centimeter. 0.16 centimeter. Okay, meter. So 0.1 meter actually means 10 centimeters. So out of this 16 centimeter, the middle is 8 centimeters. Okay. That is not where you are getting the zero potential. You are getting the zero potential slightly this side. If this is the middle is 8, this is 10. So it is coming 2 centimeters to the right of the middle. And you can understand why. That is because this has more power. This is more charge. No? So hence it can create a bigger potential, okay, at a smaller distance. At an equal distance, if you take both, this will create a more potential than this. So it cannot become zero at the middle. As you go further and further, the potential due to this will reduce and potential due to this will increase. So at some point, they balance out. Okay. So where they balance out, they cancel and give you zero. So that is the understanding that you need to have. The understanding here is the potential from here keeps reducing when you go further. But when you go towards this, potential due to this will keep increasing. At some point, they become equal. And that is the zero point because one is positive, another is negative. I hope you understood. Okay, now the point basically I am wanting to make once again is now it is possible that there may be some point this side or this side. Also, there can be another point where the potential is zero. Okay. Now think about it. Will it be this side or will it be this side? That we have to figure out. Okay. So since this is a smaller charge and this is a bigger charge, since that is a smaller charge and this is a bigger charge, the possible so the bigger charge actually is going to basically die down slowly like this. Smaller charge is going to die down like this. So they will become equal somewhere here. But this side it is actually not possible at all. Bigger charge will have more effect. Okay, so you think about like having a brighter bulb and a lighter bulb. That like that you can think. Okay. So it has to be on this side. So for it to be on that side, we don't know where that is, but we can now take this here as some point Q where that is true. So if that point Q is true, so how to calculate that point? So only difference in that case is from here, basically, it is this plus x, correct? So that's one of them is x. Okay, one of them is x. Okay, let's take it as for example, uh, this from here itself we call it as x. Let's call this one as x. Okay. So the other one will be in that case x minus from here to here will be x minus 0.16 x. So see what we are doing now is we are assuming that it will happen on this side and we are basically calculating at what point it will happen. So we are taking let it be x. From here it is always I am calculating the distance from here x. From here also you can do. Okay. But I am doing it from here x. From here in that case it will become total x is this. This is 0.16. This has to be x minus 0.1. Now all the other procedures basically remain exactly same. The first part will be basically calculating that we see this x may be different from that x, the value of x, but still we call it x. So this is still 450 by x, same ish. Okay. And here instead of 0.16 minus x, this would become I'm going to alter here only just to show you basically how this it will be in the similar way. So this will become x minus 0.16 instead of 0.16 minus x. This also will become x minus 0.16. So this is x minus 0.16. So I'm just basically modifying the same thing just to show that it is exactly the same thing. So here again same thing. Numerator is you can see that it is not at all getting changed. As it is coming. Okay. Only denominator is getting changed. X minus 0.16. So this also will become now x minus 0.16. I hope you are understanding what we are doing. Okay. Now this will become plus 5x minus 0.8. Correct? So now what I'll do is basically I will get this minus 0.8 this side and 3 this side. 5x minus 3x is equal to 0.8. Okay. 5x minus 3x is nothing but, I'll write it, x minus 3x is nothing but 2x is equal to 0.8. So x is equal to 0.8 by 2, which is nothing but 0.4 meters RT centimeters. So you can very clearly see now here that this one is 16 centimeters from here to here. So instead of now that 16 centimeters, you go for some more distance, like for another 24 centimeters. You go. At that point, you see the charge, the potential due to this and potential due to this will be exactly same and they cancel. When they cancel, it will be zero. So you're going to get zero potential. So we have found out 2 points. The answer to this is 2 points P and Q at a distance of 10 centimeters and 40 centimeters respectively from the first charge are at zero potential. This is the answer. Okay. Now you may be a little bit sometimes confused because if somebody has taken x from this, if they have noted x as from the charge B, then they would. So that's why diagrams are very important. From where you have taken x, important. If you have taken x from the other side, since you have got 10, you would have got here x as 6 centimeters. Because from one side, if it is 10, the other side has to be. So similarly, here also you would have got 24 as the answer because 40 minus 16. So depending on where you have chosen x, you will get a different answer. Okay, if they want you to give the perfect answer which they are asking, then they would specify basically from the charge A how far it is. So here they have not uh, they are not asking that question. So you can choose to basically write down from which charge you write yourself, so that you'll be very clear about from where. So the diagram will give you the very clear understanding of from where we are taking the x distance now. So I hope you understood this answer. I took a little bit more time to explain this mainly because uh, you have to understand the whole concept along with solving the problem. So you can actually take this down, write it down, or I will just go away with 1 second so you can take a pause here and take a screenshot. Okay. So I'm going to erase this and go for the next problem. So write down a parallel plate capacitor. So the next question is a parallel plate capacitor with air between the plates has a capacitance of 8 picofarad. So we are basically writing whatever here there here. What important words we are writing. Okay. One is it's a parallel plate capacitor. It's an important information. Okay. Because formula is there for a parallel plate capacitor for us. Second thing point they are talking about is there is air in between them. There is air in between them. So since there is air in between them, see the inputs that are given, the data that are given in the question need not be only in terms of numbers. So in terms of these words, data is given here. The word is basically there is air in between them. Air in between them means we have to consider epsilon naught and not the relative, not the relative permittivity or dielectric constant. We don't have to consider dielectric constant. For air, dielectric constant is considered 1. Okay. So the capacitance value they have given as 8 picofarad. So 8 picofarad means you should know the meaning of pico. Pico is 10 to the power of minus 12. 8 into 10 to the power of minus 12 farad. That is the picofarad. What will be the capacitance if the distance between the plates is reduced by half and the space between them is filled with a substance of dielectric constant 6? What we are doing is there is a certain distance. Okay, let's say distance between them is d. Distance between them, distance between the plates. Between the plates is initially d. So we don't know whatever it is. Okay, it is d. So this is our case A. Case A. So in case B, what we are saying is that we have reduced the distance by half and we have introduced the dielectric constant of 6. So that means case B, in case B we are asking dielectric constant is 6 and the distance between plates has been reduced to d by 2, reduced by half. Okay. And we are also asking space between them filled is fine. And what is the capacitance? C is what? So this is CA, this is CB. Okay. Now to solve this problem does not require actually any kind of a diagram. It is a straightforward, simple problem. Okay. You can visualize it in terms of two capacitors are there, air in between them, or you filled certain material in between them which has a dielectric constant 6. Okay, so two scenarios. Now in the scenario 1, so parallel plate capacitor means we have a generic formula. So parallel plate capacitor formula is C is equal to epsilon naught A by D. C is equal to epsilon naught A by D. Okay. Now, in the case of first one, the case scenario of case A. So case A is nothing but CA is equal to epsilon naught into A. See, they are not changing the area. So only distance between them is reduced. Okay, so they are not changing the area. So the formula is K into epsilon naught A by D, where K is the dielectric constant. So in the case of case A, since it is air, K is 1. Okay, so epsilon naught A divided by D. That's all. That is the case A. Okay, case and this value they have already given. It is as 8 picofarad. They have given it as 8 picofarad. They have not given the values of A and D. We know the value of epsilon naught, 8.8 10 power minus 12 we know. But we are not going to put and struggle with those numbers. Okay, unless it is necessary, we are not going to substitute the value. Okay, we have learned it by hard work, right? Now case B, CB is equal to epsilon naught B, if K into epsilon naught into A by D by 2. So here the value A is nothing but 6 epsilon naught A by D by 2, right? So we have said that it has become D by 2. So now I will go and further simplify a little bit, saying that denominator of the denominator goes to numerator, it will become 12 epsilon naught A divided by D. Okay. But we know that epsilon naught A by D is 8 picofarad. Okay, the value, if whenever we multiplied epsilon naught into A divided by D, when we did whatever the value of A and D that has been there, you got a value of 8 picofarad in the first place, right? So if you take these and multiply again, here also, since the values have not changed, the capacitance value will change. But value of epsilon naught, value of A and value of D is same. Though the distance between them has become D by 2, original value of D is same. Okay. So this basically becomes 12 into 8 picofarad. Correct? So that means 96 picofarad is the answer. That is all. See, it's a very simple problem. We didn't have to actually do too many calculations. The only thing we did was, whenever we took two situations, and in one situation this is the value, in second situation we have to calculate the value, and we have used the first situation to calculate the value. Yeah, this is basically what we talk about for the first simple problem of the capacitor. Okay, write it down, and I will give some space. You can take a snapshot if you want to. Okay, so let's go to next problem. So three capacitors. Next one, third one, you write. Three capacitors, each of capacitance 9 picofarad, are connected in series. So there are three capacitors. Yeah, that is one information. Three capacitors. Yeah. What is the each of the capacitance? Capacitance of each one is 9 picofarad. Picofarad means how much we already know. We don't have to worry about that. Are connected in series. So that is another information. Series. Three capacitors connected in series. Correct? Now they are asking A. What is the total capacitance of the combination? A. Total capacitance. Let me call it as C effective. The total capacitance, C total, whatever you want to call CT, just is equal to what? Second point is, what is the potential difference across each capacitor if the combination is connected to a 120-volt battery? What is the potential difference across each capacitor if the combination is connected to a 120-volt battery? So B is, they have said that V is total, V is 120 volt. So they want to calculate V for each one of them. Okay, let's say there are three capacitors, V1 comma V2 comma V3 is equal to what? So they seem to be equal because capacitance is equal. Anyway, so we will calculate those two. Okay. So first thing here we will draw one diagram to get an idea. Okay. So there are three capacitors. So let me call it as, in series they are. Okay. So C1, C2, C3. It so happens that all C1, C2, C3 are all same. Okay, so C1, I will write it as C1 is equal to C2 is equal to C3 is equal to 9 picofarad. Each one is 9 picofarad. Correct? So the question is basically now what is the effective capacitance? If I want to find out the capacitance of this CT it is called. So what we will do generally is whenever we talk about total capacitance or effective capacitance. So this first of all this is connected to a 120 volt battery also. Okay, 120 volt battery. So this is total V. Okay. Now effective capacitance means I should be able to replace this with a single capacitor. So that is called effective capacitance. And it must have the exactly same effect on the circuit. That is called effective capacitance. So for series combination, the formula is C effective capacitance or C total capacitance is equal to, okay. So if it is a, remember this, there are, we have two formula, one for series, one for parallel. Okay. So for parallel we add, for series we don't add. Okay. We have formula like this: 1 by CT is equal to 1 by C1 plus 1 by C2 plus 1 by C. This is for the parallel series capacity. Whereas in resistors, we actually add when they are in series. But in capacitance, we don't add. We basically take the reciprocals and get the reciprocals. Okay. So now 1 by CT is equal to this much. So in our case, all of them are 9 only. So I'm still keeping everything in picofarad. So this is nothing but 3 by 9, or it is equal to, so I'm just adding 1 by, correct? So this is nothing but 1 by CT. So CT has to be 3 picofarad. So if each one is 9 picofarad, when you connect them in series, it actually has reduced. Just watch that. When you connect capacitors in series, capacitor total will reduce, not increase. Okay. So 3 picofarad is the total. Now that is our part A. This total. Now the question is second part, which is if you apply 120 volts, what will be the voltage across each capacitor? So since they see capacitance basically are equal, each one is equal. Okay. So what is the relationship between capacitance and voltage? So we have this formula called Q is equal to CV. That means charge on the capacitor is equal to capacitance into the voltage, or C is equal to Q by V. That is the definition. So, however, we know that since it is in series, all the capacitors have exactly the same charge. The charge is same for all of them. So, since all of them have the same charge, now this and same capacitance and potential across each one of them, let us say this is V1 and this is V2 and this is V3. So, if you look at it, basically V1 plus V2 plus V3 has to be equal to 120, correct? All of them, if you add it, they have to be equal to 120. So that is the total. Now, what is V1? V1 is equal to, see, Q by C1, correct? Q by C1. What is V2? Q by C2. Because Q is same for all of them. So we could have written Q1 by C1, Q2 by C2. But Q being same, everywhere it is same. Q by C. So this basically is nothing but 120. Now I'm going to basically take Q common, and this whole 1 by C1, 1 by C2, 1 by C3 I have already calculated. This to be equal to 1 by 3, correct? So this will be nothing but Q by 3 is equal to 1. So that is total divided by total capacity is nothing but what? 120. So if we want to basically do it individual, we're just trying to show that total capacitance here and total charge, if you take, you will get the 120. Yeah. So this is the way we proved actually also for. I mean, this you don't have to do this part to be able to do this. In our case, what we have to do is since each C is same, since each C is same, V1 is equal to Q by C1, Q by C, Q by C, Q by C. So all of these are basically Q by C, correct? So this is nothing but 3 into Q by C is equal to 120. This is capacitance of, this is the voltage of one capacitor. 3 into, this means 3 into V1 is equal to 120. V1 is equal to 40 volts. And V2 also is equal to forward thing. I just went through the process, but you know that if the capacitance is the same, equally voltage has to be divided. If you have to divide the voltage equally, that means basically 120 will become 40, 40, 40. So equal division, and hence it will become 40 each one. So that is the answer. Okay. Okay, let's go to the next one. So next one is again three capacitors are there. So three capacitors are connected in parallel. Okay. But these three capacitors have different values. Three capacitors are connected in parallel. Connected in parallel. So they have different values. C1 is equal to 2 picofarad. C2 is equal to 3 picofarad. And C3 is equal to 4 picofarad. So we have three capacitors. 2 picofarad, 3 picofarad, and 4 picofarad are connected in parallel. What is the total capacity? So I'll write it as this first part. C total capacitance is equal to what? Okay. Second part. Determine the charge on each capacitor if the combination is connected to 100 volt supply. So second part is V is equal to 100 volts. Calculate Q1, Q2, and Q3 individually, how much they are calculated. Here they are not going to be equal because capacitances are already different. Okay. So now again, the simple diagram will do that. So there are three capacitors connected in parallel, and they are all connected together into 100 volt supply. So one of them is 2 picofarad, other one is 3, other one is 4. So in parallel capacitors, if you connect the capacitance in parallel, the total capacitor is equal to C1 plus C2. Very straightforward. 2 plus 3 plus 4, which is equal to 5 plus 4 is 9. Okay. So capacitances get added if they are actually connected in parallel. It is the combination. Now, so we want to calculate what is the capacitance, what is the charge on each capacitor. Okay, so if you look at this 100 volts is appearing between these 2 points. So that same 100 volts is appearing for the one, second, and third individual. So individually, each one will have 100 volts because they are in parallel. Whenever things are in parallel, potential difference across them are same. They are not going to be different. Okay. So now if you say that first one, what is this is Q1, this is Q2, this is Q3. Okay. So Q1 is equal to C1 into V. Okay, C1 into V and Q C2 into V is equal to CV. No? So Q2 is equal to C2 into V and Q3 is equal to C3 into V. V1, V2, V3 are all same. So V. So C1 into V means what? 2 picofarad into V is 100 volts. Okay, this is 10 to the power of minus 12. So this is into 10 to the power of 2. So it will become 10 to the power of minus 10. So this is nothing but 2 into 10 to the power of minus 10 coulombs. This is 12. Picofarad is minus 12 and this is plus 2. Minus 12 plus 2 is minus 10. So 2 is as it is. So similarly, here you can write it as 3 picofarad into, so 3 picofarad is 3 into 10 power minus 12 into 100, which is equal to 3 into 10 power minus 10 coulomb. This one is 4 into minus 10 to the power of minus 12 is equal to 4 into 10 power minus 12. So this is the charge on each capacitor. Okay. If you want to find out the total charge, you just have to add all of that is the total charge. So this is how you can solve some of the problems in the parallel plate capacitors. Okay. So let me so we can also do one more problem. I think we have another 5-10 minutes there. So we'll finish one more problem. Okay. So the next problem is in a parallel plate capacitor. Again, it is a parallel plate capacitor. Parallel plate capacitor with air between the plates. Again, it's air. Air is there. Each plate has an area of 6 into 10 power minus 3 meters square. So area is equal to 6 into 10 power minus 3 meters square. Okay. And distance between the plates is 3 mm. Distance between the plates is 3 mm. 3 millimeter actually means 3 into 10 power minus 3 meters. Calculate the capacitance of the capacitor. Okay. Calculate the capacitance. P is equal to how? And capacitor is connected to a 100-volt supply. What is the charge on each capacitor? So V is equal to 100 volts. So Q is equal to how? That's the question. Okay. So this is a very straight question. The formula is already there. C is equal to epsilon naught into K A by D. This was 8.85 into 10 power minus 12, and the K is 1 here because the constant, it is basically dielectric constant for air is 1 into area is 6 into 10 power minus 3 divided by D. D is 3 into 10 power minus. Okay. So this is the capacity. So we can actually simplify it in the sense that 6 into 10 power minus 3 in the numerator and 3 into 10 power minus 3 in the denominator will basically be 2. That's all. So 2 into 8.85, which you can multiply. Okay. So 2 into 5 is 0, 2 into 8 is 6, 2 into 8 is 16 plus 1, 17. So 17.6 into 10 power minus 12 farads, or we can say 17.6 picofarad, the capacity. Once you get the capacitance, then you can calculate the Q using Q is equal to C into V, where C is 17.6 into 10 power minus 12 and V is 100. So this is 17.6 into 10 power minus 10 coulombs. So you got both Q and C. This is how we can quickly calculate the capacitance. And so basically, in the case of capacitor, you need to remember only one formula: Q is equal to CV, and you need to know parallel and series combination, which you know anyway by even in the case of resistance. This is the inverse sum. That is, so if you know this much, you can solve most of the problems in the capacitance. So I will basically end it at this point. Thank you.